Look at your hand. Its calcium was forged inside a star. The iron in your blood came from a supernova. Every carbon and oxygen atom passed through a stellar furnace. Those atoms crossed space and eventually became you. You have heard that story. But what made the stars possible? Something unseen that neither shines nor reflects light. Remove it, and stars barely form. You do not die. You are never born. Would you exist without dark matter? Our investigation begins with a galaxy that refuses to obey the visible evidence. In the 1970s, astronomer Vera Rubin measured how stars orbit inside spiral galaxies. A galaxy resembles an enormous spinning disk. Gravity should make stars near the center move faster, and stars near the edge move more slowly. That is what happens in the solar system. Distant planets take longer, slower paths around the sun. But Rubin found something impossible. Stars far beyond the bright center were moving almost as fast as stars farther in. At those speeds, the visible galaxy did not contain enough gravity to hold itself together. It should have torn apart like riders thrown from an overspeeding carousel. Instead, galaxies have turned steadily for billions of years. Something massive was gripping them from places where telescopes saw nothing. The first clue was not an object. It was a missing weight. One clue can be a mistake. But this invisible hand left fingerprints across the entire sky. The first fingerprint is bent light. Gravity curves the path of light passing through a massive galaxy cluster. Background galaxies stretch into arcs, multiply, and brighten as if the cluster were a colossal glass lens. Astronomers can use that distortion to weigh the lens. The visible stars and hot gas account for only a fraction of the required mass. The missing mass cannot be seen, yet its gravity is bending the light in front of us. The second fingerprint is the oldest picture in existence, the cosmic microwave background. It shows the universe about 380,000 years after the Big Bang, when light first traveled freely. Tiny temperature patterns across that ancient light preserve a precise inventory of what the young universe contained. Without a large reservoir of invisible matter, those patterns would not have the sizes and strengths we observe. The third fingerprint is the most dramatic. Two galaxy clusters caught after a head-on collision. Their ordinary gas collided, slowed, and heated until it blazed in X-rays. But gravitational lensing showed that most of the mass had passed straight through and moved ahead of the gas. The visible matter and the gravitational mass had separated. The scene is called the bullet cluster. Three independent trails, rotation, ancient light, and colliding clusters, all lead toward the same unseen suspect. Scientists gave the suspect a name, dark matter. Dark does not mean black. It means dark matter does not exchange light with us. It does not shine, reflect, or block a beam in the usual way. As far as we can tell, it speaks to the visible universe mainly through gravity. We still do not know what it is. It may involve particles never detected in any laboratory. If so, vast numbers could be passing through Earth and through your body without leaving any sensation. Its identity remains unknown, but its cosmic abundance is measured remarkably well. About 5% of the cosmic energy budget is ordinary matter. Roughly 27% is dark matter, and about 68% is dark energy. Dark matter, therefore, outweighs ordinary matter by more than 5 to 1. Every star, planet, ocean, city, and living body fits inside the small, ordinary slice. The dominant matter in the universe is the part no eye has ever seen. Now the real question begins. What did this invisible substance do for you? To answer, we must return to the first minutes after the Big Bang. The young universe was an almost uniform ocean of extreme heat, filled with matter and radiation. To build stars and galaxies, tiny dense regions had to grow denser, pulling in more material until gravity won. Ordinary matter faced a serious problem. Electrons, nuclei, and light were locked together in a bright, opaque plasma. Whenever ordinary matter tried to gather, radiation pressure pushed back. It compressed, rebounded, compressed again, and rebounded again, an acoustic struggle written into the microwave background. Ordinary matter wanted a clump, but light kept it tied close to the starting line. Dark matter did not have that problem. Because it did not couple to light, radiation could not push it back. While ordinary matter oscillated in the luminous plasma, dark matter began falling into the slightly denser regions. Quietly, invisibly, it gathered into clumps and filaments, the first gravitational skeleton of the cosmic web. At the intersections of that web, dark matter built deep gravitational wells. This was a race. Ordinary matter was trapped in light. Dark matter was already running. Its head start lasted hundreds of thousands of years, and that lead changed everything that followed. About 380,000 years after the Big Bang, the universe cooled enough for electrons and nuclei to combine. Light escaped the plasma and began the journey that would end in our telescopes as the cosmic microwave background. Ordinary gas was finally free to fall under gravity. And when it looked around, half the work had already been done. Dark matter had prepared a universe full of gravitational valleys, channels, and wells. Ordinary gas streamed down that invisible landscape like water flowing into a river basin. At the bottoms of the wells, gas accumulated, compressed, and heated. Eventually, the densest clouds ignited, and the first stars began to shine. Stars did not appear from an empty, featureless fog. They formed inside cradles that dark matter had prepared. Now let us rerun the universe and remove dark matter from the opening frame. The Big Bang still happens. The hot, nearly uniform plasma still fills space. Ordinary matter remains locked to radiation until the universe is about 380,000 years old. But now no invisible runner has gone ahead. No cosmic web is waiting. No wells have been dug. When ordinary matter is released, it faces an almost featureless expanse and must build every concentration from scratch. Its initial variations are tiny. Its gravity is weak. Its start is desperately late. And it is racing an opponent that never stops. The expansion of space itself. Gravity tries to gather matter. Expansion increases the distance between unbound regions. In our real universe, dark matter's early growth gave gravity enough of a lead for rich structures to form. In the dark matter-free version, ordinary matter begins too late and grows too slowly. Before many regions can become dense, cosmic expansion leaves them farther apart and more dilute. The result is not necessarily absolute emptiness. Given immense time, some sparse and impoverished structures might still appear. But the abundant web of clusters, galaxies, and stellar nurseries that fills our sky would be profoundly suppressed and delayed. Place the two universes side by side. One flowers into a luminous web. The other remains a thin, dark, almost uniform mist. That difference is the distance between a cosmos full of possibilities and one too barren to build you. Now follow the broken chain back toward your own body. Without dark matter, the early gravitational wells are missing. Without those wells, ordinary gas gathers far less efficiently into dense stellar nurseries. Without rich generations of stars, the universe loses its great chemical foundries. The Big Bang produced mostly hydrogen and helium, with only traces of lithium. Carbon, oxygen, nitrogen, calcium, and iron had to be forged inside stars and spread through space by stellar death. Fewer stars mean far fewer heavy elements. Fewer heavy elements mean fewer rocks, metals, complex molecules, and worlds. Without those materials, there's no Earth like ours, no ocean chemistry, and no first self-copying molecular system. No dark matter. No cosmic web, no rich galaxies, no generations of stars, no heavy elements, no rocky planet, no life, no you. This does not mean that you die. It means that from the universe's earliest moments, the path leading to you is never built. We often say that a human being is made of atoms. Today, that description is no longer enough. You are not only made of matter. You are made of structure, of matter arranged across many levels of cosmic history. Atoms became stars. Stars made elements. Elements became planets. And planetary chemistry became a mind capable of asking where it came from. That sequence required an order that allowed matter to gather rather than remain smooth and scattered. Dark matter is the gravitational foundation of that order. It does not shine, yet helped make everything that shines possible. Hidden in the background, it helped turn an almost uniform plasma into stars, planets, Earth, and the person listening now. Pull the camera away from one human face, past a city and Earth, beyond the solar system and the Milky Way, until the full cosmic web appears. You cannot see the scaffold with your eyes, but you may be one of its most complicated works. So, would you exist in a universe without dark matter? Almost certainly not in anything like the form you know. Not because you vanish, but because a universe capable of producing you is never given the same chance to grow. That may be one of the most humbling facts we can learn about ourselves. We call luminous things matter and visible things real. Yet most matter in the universe belongs to an invisible realm. And that invisible majority helped create every visible thing we have ever loved. The next time you look at a clear night sky, remember that the gravity gathering those stars is not confined to the points of light. It extends through the darkness between galaxies, through regions your eyes interpret as empty. That darkness is not empty. That darkness is part of where you came from. We have followed the invisible matter that helps pull the universe together. But another unseen component is pushing cosmic expansion faster. Dark energy fills roughly 2/3 of the cosmic budget, and it may decide the ultimate fate of everything. That is the next case in the invisible universe.